Welcome back to another explainer. Today, we're basically embarking on a scientific detective story. We're going to use the sheer power of thermodynamics to solve a mystery that is quite literally hiding in plain sight. I'm talking about the everyday physics of the vacuum-insulated thermos. If you're the kind of person who just loves figuring out how the world actually works, well, you are definitely in the right place. Let's get into it.
Okay, let's dive right into this. So just picture a standard ceramic mug filled with hot coffee sitting right at 90 degrees Celsius. Give it just 1 hour, and boom, it's plummeted to a seriously disappointingly lukewarm 25 degrees. But check out the thermos sitting right next to it. It also starts at that piping hot 90 degrees, but incredibly, 12 hours later, it's sitting pretty at 85 degrees. How crazy is that?
And that brings us to the absolute central mystery of this explainer. How exactly does the thermos just defy the natural flow of energy? I mean, to the untrained eye, it honestly looks like it's just breaking the fundamental rules of the universe. But to solve this case, we first need to understand what those rules actually are. Now, what's really interesting about this next part is we have to bust some major misconceptions before they derail our whole investigation. Red alert here, folks. First off, there is actually no such thing as cold moving into your coffee. Seriously, cold is literally just the absence of heat. It's the heat energy that's escaping, not the cold creeping in. Second, and honestly this trips so many people up, a thermometer doesn't actually measure the system it's placed in. Actually, scratch that. A better way to say it is it measures its own surroundings. The glass and the liquid inside the thermometer, they absorb or release heat until they reach thermal equilibrium with whatever they're physically touching. Which brings us to the absolute core rule governing our whole mystery here, the zeroth law of thermodynamics. This law is pretty straightforward. It states that energy always flows from areas of high energy, so the hotter object, to areas of low energy, the colder object. And it doesn't just stop randomly because it feels like it flows continuously until thermal equilibrium is reached. That just means both objects eventually end up at the exact same temperature. Heat is just completely relentless in its pursuit of balance. Let's break down exactly how this inevitable balancing act operates. It basically happens in 3 clear steps. Step 1 is contact. You've got a high-energy hot block and a low-energy cold block coming together. Step 2 is transfer. The heat naturally flows directionally straight from the hot to the cold. And finally, step 3 is equilibrium. That transfer just keeps on going until the particle speeds across both blocks become completely 100% uniform. And this brilliantly illustrates what that looks like in the real world. Let's say we have a 50-degree test tube and a 10-degree test tube, and they're both sitting in a 20-degree water bath. According to that zeroth law we just talked about, heat must flow predictably downwards. So the 50-degree tube loses its heat to the 20-degree bath, and at the exact same time, that 20-degree bath is losing heat to the 10-degree tube. High to low, always, no exceptions. So if heat always wants to escape our hot coffee to balance out with the cooler room, the big question is, how is it traveling? Well, it's time to identify our suspects. There are exactly 3 specific methods, 3 pathways really, that our heat energy might be using to flee the scene. All right, let's look at the lineup of our 3 suspects. First up, conduction. This is transfer through direct physical contact. Think of it like burning your tongue on a hot spoon that's been sitting in a mug. Ouch, right? Second is convection. This is transfer through the actual movement of fluids, so either liquids or gases, caused by changes in density. And finally, radiation. Now, radiation is super fascinating because unlike the first 2 suspects, it actually requires absolutely 0 physical matter or particles to travel. It operates entirely through electromagnetic waves. But for our coffee's heat loss, let's really focus on our 2 primary suspects, conduction and convection. Now, while they definitely operate differently, one through direct touch and the other through fluid currents, notice what they share. They both heavily rely on physical matter to travel. They absolutely need physical particles to bump into each other or to carry that thermal energy away. Definitely keep that in mind. It is a vital clue for later. So the crucial point is, to really understand this crime scene, we've got to map out the territory. In thermodynamics, we have the system. That's just the specific object we're studying, which in our case is the hot coffee. Then we have the surroundings. And the surroundings are literally everything else in the universe that's interacting with it, like the ambient air in the room. And right there, separating the 2, is the boundary. Now, these boundaries totally dictate what type of system we're dealing with. An open system, like a boiling pot of water with no lid, well, that freely exchanges both matter and energy with its surroundings. Then you have a closed system, like a tightly sealed mason jar. That stops matter from leaving, but the thermal energy, it can still easily pass right through the glass. But our thermos? Well, it falls into the rarest category of all, the isolated system. Our thermos is basically attempting to be the ultimate isolated system. It's specifically designed to completely block all physical exchanges of both matter and energy with the rest of the universe, all just to protect its internal state. It is literally trying to put up an impenetrable wall against the zeroth law. To truly crack this case, though, we need to shift our focus to how we actually track the thermal energy that's attempting to cross these boundaries. We have to ask, is the energy moving in or is it moving out? We track this by labeling the directional flow. In an endothermic process, the system actively absorbs heat from its surroundings. It's kind of like holding a melting ice cube in your bare hand. Your hand is losing heat to the ice. But our cooling coffee mug? That is an exothermic process. It's releasing its thermal energy out into the surroundings. Whenever an exothermic process happens, you see a very clear drop in potential energy as that heat is lost. And guess what? Our thermos is trying to stop this exact exothermic drop from happening. All right, we have all the pieces of the puzzle right in front of us. We know the relentless laws of heat flow. We know the key suspects, conduction and convection. And we know the thermos is trying to act as an isolated boundary. It is finally time to synthesize all of our scientific evidence and solve the mystery of the thermos once and for all. Let's move to the boundary of the thermos itself and see how this all builds together. If you look really closely right between the inner and outer walls of a thermos, you'll find a vacuum gap. Now, this gap is not filled with molecules or compounds or mixtures. It is, quite literally, empty space. We're talking 99.9% completely devoid of any physical matter whatsoever. And here is the ultimate verdict. Remember how we established earlier that our prime heat-stealing suspects, conduction and convection, absolutely require physical matter to travel? Well, because that vacuum gap has virtually no particles, it acts as an absolute physical blockade. Zero conduction, zero convection. The thermal energy inside that hot 90-degree coffee literally has no physical pathway to flow out into the cooler 25-degree room. Case closed, my friends. The energy is physically trapped. But, to fully appreciate what's really happening here, we have to recognize one more absolute universal rule. The first law of thermodynamics loudly declares this. Energy in the universe is transformed from one form to another, but it is never destroyed. This rule perfectly explains the true stakes of our blocked thermos. The total amount of matter and energy across a system and its surroundings always remains perfectly constant. Basically, what a system loses, the surroundings must gain. But since the thermos boundary completely blocks that transfer, the energy literally has nowhere else to go. It can't just vanish into thin air. Just think about the last time you used a chemical hand warmer on a freezing day. That's the first law in action right there. The chemical energy stored inside that little pouch is transformed into thermal energy, which then transfers right across the boundary to warm up your cold hands. So whether we're actively blocking heat with a thermos or we're deliberately releasing it with a hand warmer, the universe's equation is always perfectly balanced. Total initial energy always equals total final energy, every single time. And honestly, that's what makes this whole thing so fascinating to me. We can zoom way out from the everyday mechanics of just a simple hot cup of coffee all the way to the cosmic scale. The exact same immutable laws that keep your thermos hot for 12 hours are the exact same laws governing the entire universe. Energy might change form, and sure, it'll always try its hardest to move from high to low, but the total energy of the universe, it is wonderfully, beautifully constant. So I'm going to leave you with this final, kind of mind-bending thought. If energy can truly never be destroyed, but only transferred into its surroundings, where exactly did the thermal energy from that forgotten cold cup of coffee sitting on your desk yesterday ultimately go? Think about it. Thanks so much for joining me on this explainer today, and hey, always keep questioning the science of the everyday world around you.